blast fragmentation in MyPal, and then we will have an overview over the models. Then I'm going to speak about the gamma-based KCF model, and then we are going to investigate about the shortcomings and also the areas that I'm going to modify this, and finally I'm going to make some conclusions. Well, as you may know, drilling and blasting is the most efficient option for mining, for breaking rock mass, and at least for hard rock mining. And rock fragmentation can be considered as the most important aspect of blasting practice. And according to Kanchibotla, the economics of many operations in the mineral industry depends on the fragment size distribution, and blasting is usually the first step in giving the size distribution. And MyPal fragment size refers to the size of fragments within the MyPal after blasting. And according to McKinsey, if we want to have an optimized blast design, we need to, the first step is being able to predict fragmentation. Well, in designing a blast, we are faced with two sets of parameters. The first group are drill hole geometry, like as you can see in this picture, bench height, burden, spacing, sub-drill, stemming, and all geometrical parameters. And then we have explosive related parameters. Explosive related parameters means, for example, what kind of blasting agent you are going to use. Are you going to use ANFO or emulsion, or how many boosters, or what kinds of boosters are you going to use? And in terms of uncontrolled load parameters, we have physical and geomechanical properties of rocks that in rock blasting we may generally use rock mechanical parameters. Or imagine that this is a blasting block. Well, to do a blast, first we need to drill a hole through the rock mass. As you can see, here I'm going to show you a typical blasting practice. So we send a pentolite as the primer to the bottom of the hole, which is connected to the nonal or cortex and the role of nonal and cortex is to initiate the pentolite, and then we fill the rest of the hole with the ANFO, generally with the ANFO-based explosive. As you can see in this picture, here we have ANFO prills. And then to provide enough confinement, we fill the rest of the hole with the stemming material, generally the waste of the drilling. And if here we have the top, for example, the top view of the pattern in 3 rows, and then we blast it in, for example, in a row by row sequence, and then we have a MACPA, which contains a wide range of particles, which may vary from sub-millimeter to over a meter. And two sizes are so important in blasting. 80% passing size, because this size is a good index and has effect on the downstream processes, and also the median size, which is so important and helps us in predictions. Well, in terms of fragmentation measurement, we have 2 options. The first option is to sieve whole of the MyPal, which is not practical. It is so time consuming and also expensive. Another option, if we want to insist in sieving, is to sieve a portion of this, which I assume that it doesn't still guarantee that we can have the representative size distribution of the MyPal. Also, it has the former drawbacks. Another option, which is somehow accepted and generally engineers use to use image analysis techniques. And for this practice, you need to take your digital camera and take several photos from the surface of micro, and even at different stages of loading and hauling, to provide some representative pictures. And then you use these pictures as input of the software. And for my measurements, I use a split desktop, and you need to patiently delineate the particles. And for example, for the parts that are not recognizable and you cannot delineate, you use if there is an option for manual consideration of points. As for example, the red part here, the more patient you are, the better results you may receive. However, finally you can have the size distribution of your mark as a measurement, and this is the method that I use to measure my fragmentation. However, the principal purpose of fragmentation models is to predict fragmentation. We have different empirical models. The most popular and well-known model is COSRAM, presented by Cunningham. Then we have CZM and TCM, both from JKMRC. CZM presented by Kanchibotla and TCM presented by Georgievic. And then we have KCO presented by Oshteloni. And finally, we have another model, which is KCF, presented by myself in 2015. In terms of, it is worth it to know that what distribution function each of these models generally use. COSRAM uses variable distribution, CZM and TCM both uses variable distribution. And KCO uses Swebrek distribution function, which is a kind of, a function presented by Swebrek, and KCF uses gamma distribution function. And the interesting part of this story is that all of these empirical models are based on, and you benefit from the equation of the Kuznetsov equation presented in 1973. But Kuznetsov equation presented in 1973 expresses the relationship between the mean fragment size and powder factor. And we have a value, which is a right factor, and as the ground becomes more competent, the value increases. And if we rewrite this equation for ONFO-based explosive, what Cunningham did, we reached to this equation for ONFO-based equation, and K is the powder factor, and S, for example, if we want to use ONFO, the value for S, which is a relative strength, should be 100. And we have a value that I'm going to explain more about this parameter. Well, about the COSRAM model, it is the most well-known, popular model among for many years, and as you can see, this model uses the Rosen-Ramler distribution function, and there is two parameters in this model: characteristic size and also uniformity index, or n value. To calculate n value, we use this equation. As you can see, the input of this formula are generally geometric parameters, because actually the uniformity index expresses the uniformity of fragmentation. And then we have characteristic size, which we can calculate by this equation. And for calculation of the median size, we can use Kuznetsov equation, as I explained before. And Cunningham modified the blastability index by Lilly and presented an equation to calculate the rust factor more accurately. Okay, about the TCM, or two-component model presented by Georgievic, here the assumption is that fragmentation, in blasting we have two fragmentation mechanisms. compressive shear failure around the blast hole adjacent to the explosive, and also tensile failure in the distance farther from the center of the hole. And it is actually kind of, it is a right idea because we have actually these two differences. And for the compressive shear failure, we have FC, which is the fraction of crushed material, and should be calculated through the chamber blasting practice. And however, due to different mechanisms of failure, separate fragment size distribution functions required. So the equation is like this, and when we are blasting in hard rock and hard massive rock, for the crushed material, we should put 0 here, and if we do this, the equation returns back to the original form of Cosmo. So here we need another additional parameters to calculate. One is blasting chamber parameter like radius, powder factor of the chamber, and also the fraction of crushed material. And here you can see that by the summation of two parts, we can have the overall distribution curve. The next model is Kreisman model, presented by contributor. The major difference between the approach, this approach and the conventional Cosram is that in this method it is hypothesized that fines are produced by the crushing action of explosive adjacent to the blast holes. And for the coarse part, this model uses the original Cosram model, and for the fines part, and uses the original n value as I explained. And for the fines part, it uses the fines uniformity of index. And also here, the percentage of -1 millimeter as a default size should be calculated to put in to be able to calculate the n fine. The fine uniformity index and the fine end of the distribution is then calculated by the substituting -1 millimeter size and the characteristic size, which is calculatable by this approach. And once the model is calibrated for a given, then it is useful to run for the several practices. But there are some issues about the CZM and TCM models. The first one is that uniformity index n value has a physical meaning to blasting engineers, which means uniform fragmentation. So high values are preferred. And high values indicate uniform sizing, low values indicate a wide range of size, including both oversized and fine. And n generally ranges between 0.8 and 2.2. And for example, dust boulders, the value drops under 0.75. And in a normal situation, it ranges between 0.75 to 1.5, and for more complex rocks, for example, the value reaches more than 1.5. However, n determines the shape of the Rosenlander curve, and the question arises that what is the physical meaning of fines uniformity index by TCM and CZM? Over here, you can see that, for example, the relationship between the n value and design parameters, for example, in terms of drilling accuracy, as the drilling accuracy increases, the value of n, which means uniformity of our fragments, increases. And here, by increasing the diameter of the hole, the value of n decreases, which means that, for example, for larger diameters, because the pattern becomes larger, we use larger spacing and burdens, so we expect coarser materials. However, the uniformity of the materials can be decreased because the distribution of explosive energy is not like tighter patterns. And in terms of fines production origin, according to Georgievic, in the case of fines, the rock factor and uniformity coefficient are determinable by the explosive rock matrix interaction in the scale of single pole blast. Where again, we see that what's the meaning of rock factor for fines? Because actually, as I explained, to calculate rock factor, we have a formulation, and we use some data like rock strength, and we involve the structure of rock and gives us information and idea about the competency of rock. But here for the fines, it again loses the definition and the original definition of the rock factor. And hence parameters determined by blasting chamber testing are transferable to in situ blasting information. And I assume that however, the results, for example, from transferring results from blast chamber to a real situation is not that correct. And corrosion along the blast hole is not constant. In terms of huge underestimation of the causal, limitation originates from the form of the Rosen-Romler distribution. And basically, say Rosen-Romler function is not a good option to estimate the fines part. And the assumption of fines production origin by TCM and CZM correctly criticized many times. And Georgievic addressed to the shortcoming with JKMRC models known as TCM and CZM and quoted, the volume of corrosion around the blast hole is only a fraction of the volume of fines observed after sieving. Accumulated experience reveals that the crushing around the blast hole is not the sole cause of fines. In many situations, it is not even the principal source of fines. However, Georgievic in his paper mentioned some sources of fines, like around the blast hole, shear failure along the in situ joints, and shear failure along the blast-induced cracks, and in-flight collision of fragments. And in terms of joints, the joint field thickness, joint field material, and shear rate of the aspirated along the joint planes are so important. And we can add other sources to this list, like ultimate MACPA rest, rolling fragments over each other. When the heave moves and is close to become settled, many materials, heavy materials, roll over each other. This can be considered as a source of fines production. And also primer and boosters utilization points. In many blasts, we use various boosters along the hole, which can be considered as a source of fines. However, we can see again in two experiments by Swan in 2003, he provided multi-layered cylinders with different colors, and as you can see, the contribution of the outer layer, which is yellow and green, the contribution of the outer layer is considerable in both practices because, however, he practiced different cylinders with different diameters. So we can see that the contribution of the outer layers is considerable, and the only source of fines is not the crushed zone around the hole. About the KCO or Cousins-Sofkanikam Oitalani model, it is a 3-parameter function. As you can see, it uses maximum x, or the maximum size of particles, and median size, and a b-value, which is a kind of curve undulation parameter. And here you can see the overall function that different parameters should be substituted. To calculate the median size, we use the original Cousins-of equation, like the other models. And he presented two equations to calculate the b-value. The former equation shows, however, the first one presented, as you can see, applies n value and was so dependent on the value of n. The second one, which showed how improved prediction of fragmentation is this equation. And in the new equation, he presented the reference B as 4 meter. And in the Sorter function, can be used in the causal model and removes 2 drawbacks. The first drawback returns back to the estimation of fines. The first drawback can be removed because of the essence of the function. And the second one, for the upper limit cutoff to the block size, Oitelodi correctly says, another weakness is that the Rosen-Rommler function in the causal model has no maximum fragment size, which any blast quite obviously does. And he introduces a parameter, the maximum x, and says if for the equation we can obtain maximum is by minimum in situ block size, or if it is not available, we can use the spacing or burden and the maximum block size. Now let's investigate in what situation, in what scenario we can have a maximum block size. Imagine that this is the pattern and we blast it in a row by row situation. In the first scenario, the first, second, and the third row fires. And as you can see, the chance of having a particle size in normal situation with the size of a spacing or burden is 0. In the second scenario, we may blast these 2 misfires in the second row, and we have complete blast in the third row. Here again, you see that there might be chance for this, but again, the chance of having a particle with the size of spacing or burden is so low. In the second scenario, the first row fires. In the second row, we have 3 misfires, and also in the third row, we may have 3 misfires. So this is maybe the only scenario that supports Oitelodi recommendation to determine spacing or burden as the maximum or top size of the fragmentation. However, in spite of all formulations, everything, B is an undulation parameter to bend the curve, like Beckham according to Now we have, I presented a gamma-based model, KCF or KCCOM. The former name was KCCOM. Now, however, it had 2 names. Causes of Shortcomings Faramarzi. So it is a gamma function, a 2-parameter gamma function, and I defined a 40% grafting point, and I really inspired from the JKMRC models because actually it is a 2-component model, and the new model is comprised of 2 similar gamma-based equations for fragment passing size less than 40% and more than 40%. And we just use the normal gamma function for the fine to central part and the central to coarse part, and K is shape parameter and theta is the scale parameter in this function. So let's see how we can do this. I replaced shape and scale parameter with appropriate experimental parameters, and then here we can have an equation for the fine to central part and another equation for the central to coarse part equation. In different trials, however, I came to this conclusion that if I use spacing and burden, I can correctly adjust to the coarse part material, and I use spacing and burden in this model, and the problem with prediction of coarse part material somehow enhanced. So we use the central to coarse part equation for the particles more than 40% passing size, and another equation for the particles less than 40% passing size. And in these two equations, I use NF, which is actually the uniformity index value with a little minor difference. I just remove the power of the original equation, and just to avoid the misconception, I use NF instead of N. Actually, the purpose is to shape the curve of my model. Well, the question arises why 40% passing size was chosen as grafting point. After investigation of hundreds of pictures in the image analysis technique, I noticed that generally the Fines cutoff associates with passing sizes less than 40%, ranging between 10 to 40%. So I decided to use 40% passing size. And later in the conference, Sanch-Durian calculated the absolute logarithmic error for various functions. And as you can see, the errors dramatically increases after 40% passing sizes. However, I use 40% passing size as a grafting point and joining two curves. So imagine that we run the two different equations with similar inputs, and we have two sets of distribution. For the coarse part, we just need this part of distribution and values. For the fines part, we need only this part, and if we connect them at the 40% passing size, actually they cross each other at 40% passing size. Because we use the values around the 40% passing size. The final distribution curve will be something like this. And I validated this model with full-scale blasting, full-scale blasts. However, because of the form of this equation, KCF generally, or KCCOM here that I have used, predicts more fines because of the form of the equation than the other ones. And I calculated absolute logarithmic error for all of the blasts. As you can see here, the performance of KCCOM is better than Swebrek and Kazan. However, in the coarse part, they were pretty good. Actually, we are so good in predicting the coarse part. But the problem starts when we want to predict the fines part, because we don't have a benchmark or any confident measurement method for this part. And another interesting thing was that even in the coarse part, the performance of KCCOM is better than the others. The reason might be because this model is established based on image analysis pictures. So, and image analysis technique is so good in distinguishing the coarse part material. So maybe this might be the reason that this model performs still better in the coarse part in comparison with Kazram and Sor. Later, I tried to predict 80% passing size with the model. To predict 80% passing size, we just need to run the central to coarse part equation. We don't need another equation. So I tried to predict 12 full-scale blasts by this model in another mine, and here you can see the results. The coefficient of correlation for 3 models was so close. Our KCCOM performed a little bit better, but actually the values are so close, we can say this is so good. Then, as you may know, coefficient of correlation is not as a sole indicator is not enough for a comparison. So I calculated root mean square error, and as you can see, the minimum or the least root mean square error belongs to KCF. But there are some problems similar to all empirical models about the KCF. The first problem is that this model is established based on really limited data, and model must be validated by more data from full scale and also experiments, laboratory experiments. Another problem is that the gamma-based model inherently predicts more finds. Still similar to all empirical models, it is incapable of giving a confident estimation of finds. And maybe the problem is that we cannot still measure the correct amount of finds within a mock bug. Another problem is that the find to central part equation is established based on image analysis results, and the image analysis technique and the split desktop is not a good option to measure the finds, and cannot be accepted as a reliable method to measure this part of materials. And again, cannot capture rock mass variability across the blasting block or along the blast hole, because generally all of empirical models are for single hole blast, and gives us an idea about fragmentation for just one blast. And modification of find to central part equation by sieve data from previous experiments can improve it and make this equation more supportable. And just to make conclusion, it is a new model with promising results. KCF didn't add to complexities, kept traditional simplicities of Qasram, but showed improvements. It has potential to become a powerful model. The proposed KCF model provides another option for prediction of fragmentation, prediction of 80% passing size, just by the central to coarse part equation is possible. And the studies are open, more practice are required to improve this model, and still a long way ahead. Thank you for your attention, and welcome any question.